Well, so once again, it's Curtis Bright from the University of London. And we're delighted to have him speak about that and lattice reduction for integer factorization.
Thank you very much. So thanks, Dr. Stephen, for organizing this. It's really my pleasure to be here. And as you mentioned, I'm a professor of computer science at the University of Windsor. And this is work that I did with a graduate student of mine who defended his master's thesis 2 months ago. And it'll be on combinations of SAT solving with lattice reduction for integer factorization. Okay, so let me start with the question. Who in the audience has used a SAT solver before? Okay, one here. Who knows what SAT is? Okay, so a lot of people, this is actually exactly what I was expecting. And one of the goals for the talk is to kind of plant a seed in people's minds about SAT solving. You know, why would you care about using SAT in your work? Okay, so SAT is the classic problem from logic of given a logical expression, can you make it true? Right, so we'll just focus on Boolean logic. So we have propositional variables, which are going to be true or false, and then you can connect your true or false variables with these classic logical connectives, right? So and, or, not, XOR, if and only if, and you can combine these connectives in any which way that you want to form a logical expression. Here's just one example here, right? So you have X or Y and not X is if and only if is true, if and only if Z is true. Okay, so the question that SAT asks is, given such an input, can you make it true? Can you find an assignment to the variables, which is going to make the formula true? So let me ask the audience, can you make this true, this formula? Yeah, so how do we do it? Anyone want to say? So assignment to X, Y, and Z, it makes it true. How would I choose for X?
You can put Y through and Z anything, and then X will be just not Z.
Yeah, so you can take Y to be true. You might as well just take X to be true. Therefore, not X to be false, and so then you take Z to be false. Right, so this is a simple one that is satisfiable. So if you can find a satisfying assignment, the formula is said to be satisfiable. If you cannot find a satisfying assignment, none exist, it's unsatisfiable. Okay, so this is SAT. And SAT is very important, right? You don't have to take my word for it. Don't take the word of Donald Knuth, right? So one of my heroes, Donald Knuth, is, he's well known for many reasons. One, he wrote TeX, which is what LaTeX is based on, right? And he also is famous for writing this magnum opus, the Art of Computer Programming series. Believe it or not, he's been writing this series for over 60 years, since the 1960s. It's funny, like in the States, right, there's a presidential election going on, and Joe Biden had to drop out because he's 81. Donald Knuth is actually 86, still growing, still strong as ever. He's writing, I think he writes every single day for the whole day almost, right? He has an immense body of work. The last version of the Art of Computer Programming came out 2 years ago. It's 700 pages long. A full half of that book, the second half of volume 4B, purely devoted to SAT. So, that just gives you a taste of how important it is. And if you kind of want a more gentle introduction to SAT, I wrote a paper in the Maple Conference 2019, linked at the bottom here, which just goes over some basic problems, just of the ones that you might want to solve, like Sudoku, right? Anyone played a Sudoku puzzle? Yeah, right. So you can actually come up with a very simple way of translating that into SAT, and then just using a SAT solver on it. Get your Sudoku answer that way. Okay, so the SAT solvers are programs designed to solve the SAT problem. Now, some people who know about the theory of SAT might be asking, well, isn't this a fool's errand? Because SAT is what's known as an NP-complete problem. And NP-complete problems, the conventional wisdom are intractable to solve. And indeed, just let me make it clear that there's no fast algorithm to solve that in the worst case, right? The algorithms that we have today, the best known algorithms will run in exponential time. And it's conjectured that there are no algorithms that will run in polynomial time for SAT. Okay, so indeed, there are cases where SAT solvers will perform poorly. However, what I'm going to, that said, I'm going to start the talk with 4 examples of just problems where people have used the SAT solver effectively. These are mathematical problems that hopefully at least one of them are of interest to you. Okay, so the first success story here it comes from Ramsey theory. So Schur was a mathematician who, about 100 years ago, proved this interesting result about coloring the positive integers. So he said, if you color the positive integers using k colors for some finite k, you must introduce a monochromatic triple. Is someone? Yeah. Oh, just want to come in. A monochromatic triple of this form: x, y, x plus y. Okay, so that means no matter how you color the integers, you must have x, y, x plus y all color the same way. Doesn't matter how many colors you use. Okay, so it's an interesting result. It was a non-constructive proof, right? So it doesn't tell you how, you know, a monochromatic triple must come about, but it proves that it always must be there. Now, that raises the question, how far can you go, right? How far can you color the integers until a monochromatic triple must exist? So here is an example. Like, let's do 5 coloring, right? So this is a 5 coloring of the integers from 1 in the upper left here to 160 in the bottom right. And this avoids all monochromatic triples of this form x, y, x plus y. So for example, 1, 2, 3 would be a triple. It's not monochromatic. And every triple of that form, it also not be colored the same way. Okay, so you can check, you know, it's tedious, but you can check this is a 5 coloring, which avoids all monochromatic triples. Now, the more interesting thing is, it actually was shown, this was a famous open problem for 100 years. It was shown in by Hule in 2018 that this is the best you can do with 5 colors. You cannot go any farther. You cannot even just try to color the integers from 1 to 161. You cannot do it. You must introduce a monochromatic triple. Now, why is this a difficult problem? Because just imagine how many 5 colorings there are of the integers, right? Even just from 1 to 161. There's an astronomically large number. So the SAT solver is somehow able to cut through that immenseness, right? It's able to prove there is no way to color the integers from 1 to 161 without introducing some monochromatic triple. Okay, second success story. This comes from projective geometry. Projective geometry is weird. It's basically a geometry where you have no parallel lines, right? So any 2 lines are going to meet at a distinct point, right? And then you have any 2 points define a line, just like normal. So this is a kind of a generalization of it's a geometry that Euclid never considered. And you can even take it a step farther and consider finite cases of this, which is kind of weird, but essentially you have 3 structures here, which are called finite projective planes. Okay, and essentially the plane is said to have order n when every line has exactly 2 points on it. So a triangle is essentially a projective plane of order 1. Okay, and you know, they get harder to draw as the order increases, but here's the open question. It's still open today. It's very famous in discrete geometry. For what orders do projective planes exist? Okay, it is known that you can construct a projective plane in any order which is a prime power, right? It is classic construction. Also, it's known that projective planes don't exist in some orders such as 6, right? No projective planes exist in 6. So the first order, which is not a prime power or 6, is 10. This is a famous problem known as Lamb's problem, after Clement Lamb, a professor at Concordia, who in the 80s proved the non-existence of a projective plane of order 10. Right, so it does not exist. However, he used a computer search, right, a supercomputer that ran for months. Okay, so you know that raises a little bit of a question: is there a bug in your code, right? Anyone who's written a computer program knows this. It's very easy to have a bug in your code, and then this could influence the mathematical result, right? It's a bit of an unsatisfying situation. Work that I did a couple of years ago was basically to solve this using a SAT solver. SAT solver used 15,000 hours to show projective plane of order 10 does not exist, and it comes with a certificate which can be verified. Okay, so it kind of puts us on a more sound foundation. We actually found a couple cases that Lamb had missed in his search. Third success story comes from actual Euclidean geometry. This is a question of Erdos. And Erdos asked, if you take a sufficiently large set of points in the plane, and let's say no three points are collinear, is it the case that the points must contain a k-hole? This is a convex k-polygon that's empty, has no other point inside. So an example here for 4 holes, right? You have 4 cases here where you have a 4-gon which is empty, right? There's no point inside. And in fact, you can prove, like, without loss of generality, these are kind of the 5 cases that you'd have to consider with 5 points, and each one of them has a 4 hole. Now, if you only have 4 points, you actually can't do this because you could have the, the kind of the Star Trek logo. You have a triangle with a point in the middle, and that's going to be a convex triangle with a point inside, right? So with 4 points, you can get away with without constructing a 4-hole, but with 5 points, you can't. Furthermore, with 10 points, you can have a more general argument where any 10 set of 10 points must contain a 5-hole. Now, you might think this generalizes, right? So for every value of k, you can take some large enough set and find it must have a k-hole. That's not the case. In fact, there are arbitrarily large sets which do not contain a 7-hole. Maybe surprising, right? But that's how it turns out. So here the question is, and this was actually answered this year, but in the paper at the bottom here, a SAT solver was used along with 17,000 hours to show that every set of 30 points must have a 6-hole. Okay, so they kind of resolve this question of Erdos, right? And this is, it's interesting, right? Because this problem has nothing to do with logic, right? It's almost surprising that a logic solver, which is a discrete nature, actually can prove things about the integers, or not about the Euclidean plane. Right. The last success story I want to just talk about is about algorithms. So let's say we're multiplying matrices, even just 3 by 3 matrices. What's the fastest way of multiplying 3 by 3 matrices? This is a very well-studied problem, right? The naive approach would use 27 scalar multiplications if you just use the definition of matrix multiplication. And people have come up with better ways to do it. In the 1970s, it was found you can actually get away with 23 scalar multiplications. You can multiply 3 by 3 matrices with 23 scalar multiplications. And people had tried to beat that, right? After, in the last 5 decades, people had tried to beat it. They couldn't, but they found 3 other algorithms which were different, but used the same number of scalar multiplications. Okay, so that was where the state of the art stood in 2021. Then this paper came out, new ways to multiply 3 by 3 matrices, and it was, depending on how you look at it, kind of a sorry day for humanity, because a SAT solver, this was encoded into SAT, they ran a SAT solver for over 300,000 hours, and they came up with 17,000 new ways to multiply 3 by 3 matrices, right? So they kind of blew humanity out of the water, right? Humans had taken 50 years to find 4 different algorithms, and SAT solver found 17,000 of them. So it's still not known if this is the best result. I talked with Manuel Cowers at a conference last month, and he's of the opinion this is the best. There are no algorithms with 22 scalar multiplications, but it's an open question. You can't rule it out just yet. Okay, so those are 4 success stories. Just hopefully they pique your interest that, these are problems which don't have anything to do with logic, right? And I could go on. I tried to choose examples which are from different branches of mathematics, just to give you a taste of, what SAT solvers are good at. Okay, so I have another question. Who's seen RSA before? Okay, got some people here, right? So RSA, it's a crypto system. Essentially, it's going to motivate integer factorization. The idea is, you buy something on Amazon, you type in your credit card information sent to Amazon. Now, you don't want somebody snooping in on your Wi-Fi or your internet provider reading your credit card information, right? So you want to keep it private. So what is done in practice is the data is encrypted in a format that only Amazon can read it, right? So even if someone's snooping in on your internet traffic, they're only just going to see the encrypted data. They can't decrypt it unless they can break, let's say RSA is being used. So RSA, essentially, the best known attack to break it in general is to factor a number of this form. It's called a semi-prime, right? N will have exactly 2 prime factors, P and Q. N will be known to everyone, right? This is a public integer. P and Q will be private. They're hidden. Only Amazon knows them. So anyone who finds either P or Q will be able to read your credit card information, right? So the whole system is predicated on the fact that integer factorization, if N is chosen properly, is a very difficult problem, as far as anyone knows, right? So, you take P and Q to be 2 relatively large primes. They have thousands of digits. They are both with the same bit length, and they're randomly chosen. Okay, so nobody knows how to factor N, and there is a caveat here, which is, integer factorization is such an interesting problem. There's a wrinkle that I don't think anyone would have expected. There's a fast quantum algorithm for solving integer factorization, right? So if you can develop a quantum computer large enough, you can actually break RSA and read people's credit card information. So people expect in the next decades is kind of a popular conventional wisdom that quantum computers will be developed large enough to break RSA factor, large integers n. Okay. Now, SAT is very flexible, right? You can reduce a lot of problems to SAT, and I'm just going to go over a very basic way of reducing integer factorization to SAT. Right? In fact, this is straight out of Knuth's book. All right, so let's say n is the number we want to factor, right? N is the semi-prime, and we know n, and so we know the binary representation of n. So in actual practice, n will have hundreds or thousands of digits, binary digits. Let's just say for a toy example, n has 4 digits, n3 to n0. Okay, so we know these binary digits. Let's say n also has 2 prime factors. In this case, for example, both the prime factors have 2 binary digits, right? So we can represent them by p1, p0, q1 to q0. Okay, well, what you can do now is set up a symbolic multiplication problem, right? This reduction is basically just based on the school book method of multiplication. No, we're not doing it with decimal numbers, we're doing it with binary numbers, but it's the same thing, right? So you set up a multiplication. These are symbolic variables. The only ones which are known are n's at the bottom, but you do know relationships between the variables. For example, a0 is going to be equal to the product of p0 times q0. Okay, these are all 0, 1 integers, and you can set up the equations are listed on the right here. Now, here's the thing, right? 0, 1 integers can easily be translated into Boolean logic. Right? You let a variable be true, and it represents a 1, and if the variable is false, it represents a 0. Okay, so what we do then, if a0 is equal to the product of p0 and q0, in a logical context, that's going to be a0 is true if and only if p0 is true and q0 is true, right? And that's just the logical expression shown at the bottom here. Right? A0 is true if and only if p0 and q0 is true. So in that way, you can translate all of these integer equations into Boolean logic expressions, and then you just give the expressions to a SAT solver, right? Each one of these can be given to the SAT solver and along with the bits of n, and then you just step back and let the SAT solver search for the solution, right? The SAT solver will take as input these expressions and find you the bits q1 to p0, which will make all the equations true and therefore give you a factor of n. Okay, so this is an interesting, it's an elegant reduction. This is what Knuth has to say about it. He says it's kind of mind-boggling, right? Because we didn't use any real number theory. It was almost brain-dead reduction, right? It's just literally just encoded a multiplication, and that's it, right? It's literally the definition of multiplication. Let the solver do all the work. So, it's elegant, but it's brain-dead, right? It's not using any sophisticated mathematics. So there is a downside here, which is this is a problem where the SAT solver is not going to perform very well, right? I gave you 4 examples where the SAT solver performs really well. But like I said, SAT solvers will reduce to an exponential time search, for certain cases. And this is one of those cases where the solver just doesn't know enough about number theory to actually make good progress on this problem. It is going to be very slow, all right? And it does not compete at all against the best integer factorization algorithm. So the best integer factorization algorithm today for arbitrary numbers is the number field sieve. And at least heuristically, the running time on an n-bit integer is going to be e to it's basically the cubed root of n. Okay, so this tilde just basically means we hide the log factors, but the bulk of the running time will be e to the cubed root of n. So this is a running time which is worse than any polynomial because we have an exponent here. It's actually better than any exponent though, right? Because it's not e to the n, it's e to the cubed root of n. So it's better than any exponential. It's what's known as a sub-exponential running time. So it is definitely going to outperform an algorithm which is purely exponential, right? And this is what we see in practice. Number field sieve will beat SAT every day of the week, even though the number field sieve itself is going to be worse than polynomial. Okay, but that is in trying to break RSA in theory, but in practice, cryptography has an Achilles heel, which is essentially that somebody has to do the decryption, right? Somebody has to know the private key. And there's many underhanded ways, hackers and cryptographers have studied ways in which you can get extra information about those prime factors that in theory you shouldn't be able to get, right? Even just timing how long the decryption process takes, that actually could leak information about the primes P and Q. There's cat attacks, there's social engineering attacks. There's many ways in which you could leak information. I'll give you one on the next slide. So, a security tip is implement your algorithms in the Platonic universe. Then you don't have to worry about all this messiness, right? About these side channel attacks. Okay, so here's the motivating example, which will motivate our work. Let's say you're using full disk encryption. This means every time you write a file to your disk, it gets encrypted. So if someone steals your hard drive, it's useless to them. They can't read your files because unless they have your private key. Okay, so what's the flaw here? Well, the side channel attack is that your computer itself has to be able to read the files. So your computer has to know what your decryption key is, right? It has to have the primes P and Q. Well, okay, but let's say the P and Q must be stored in RAM somewhere so that you can do the decryption. But let's say you've screen locked your machine. So if an attacker has physical access to your machine, it seems like there's nothing they can do, right? They could steal your hard drive, but it's useless to them without your private key. And they have, they could take your RAM, but when they disconnect it from your computer, as soon as the power is lost, the RAM gets cleared, right? And they can't log into your operating system, say it's screen locked. So what can you do? There's actually a surprising attack that was, a surprise to me. There was this paper in 2009. They actually showed that DRAM modules actually have a remnants effect, especially if you keep the temperature very, very low. Yeah, so you've heard about this, right? What they did was they actually did this in practice. They took the DRAM module, disconnected from power, stuck it in a jar of liquid nitrogen, right, to cool it down super cold, and they kept it in the liquid nitrogen for an hour. And guess what? All the data, most of the data was recoverable from the RAM. After an hour without power, it was still there because it was kept so cold. The bits were not decaying; they were actually preserved. 99.9% of the bits were preserved. So this is an attack which could actually happen in practice, right? Like, let's say you're James Bond and you're breaking into Dr. Evil's lair, right? And you get his hard drive with the plans to destroy the world, and you have the DRAM module which you can stick in a jar of liquid nitrogen, bring it back to Q, and well, what will happen? You're going to get a degraded version of his private key. Furthermore, you're actually going to know some bits with absolute certainty, because what happens in practice is bits will start to decay to a ground state. Let's say the ground state's 0. So with some probability, the longer it's without power, the more bits will start to decay. And this means since they decay to 0, they mean that when Q goes and reads the bits of the RAM, any bit with it, which is a 1, well, must have originally been a 1, right? Because bits don't decay to 1. Now, if a bit is a 0, well, it's uncertain, right? It could have been a 0 originally. It could have been a 1 which decayed to 0. So you get some bits where you are uncertain about if it's a 0 or a 1, and you get some bits with absolute certainty. So essentially, this is going to happen the decay happens essentially randomly, and you're going to get something like this, right? So let's say these are the bits of P. The red are the known bits that you'll know with absolute certainty, and then the white positions are unknown bits, right? Maybe you know it with some probability, but we're just going to assume we don't know them. Okay, so here is the problem at hand. How do we go from known bit, we have a degraded version of the private key, where at random we have some no knowledge of the private bits. How do we go about getting the rest of the bits and therefore saving the world? Okay, so the first thing you would try is the number field sieve, right? The fastest integer factorization algorithm. Well, this actually seems to be a non-starter. At least as far as anyone knows, the number field sieve can't be sped up by this extra information. It works on a different type of structure. It doesn't work on the bits of the primes. Okay, so it seems like that can't be improved on. However, the SAT approach absolutely can take advantage of the known bits, right? Because with the SAT approach, you have a variable representing, let's say, the 50th bit of P. If you know the 50th bit of P is leaked to be a 1, you just tell the SAT solver, okay, that variable corresponding to that bit is a true. And for every bit, the more information you can tell the solver about the structure, the faster the solver is going to run. And this absolutely will happen in practice, right? The more information you can tell the solver, the faster the solver will, because the smaller the search space is, actually, right? It'll simplify the formula into a shorter formula, which can be solved easier. So with enough leaked bits, the solver will actually outperform the number field sieve. However, the problem, of course, is the solver is still not using any number theory, right? The number field sieve, on the one hand, uses some very high-powered mathematics to be very fast, but it doesn't exploit leaked bits. Whereas on the other hand, the SAT solver is able to exploit the leaked bits, but it's not using any number theory, so it's going to be relatively slow. This is the question we address in our work. Can we use algebraic techniques to speed up the SAT solver on these leaked bit factorization problems? Okay, so we were able to do it using this algebraic approach known as Coppersmith's method. So Coppersmith came up with this really cool way of factoring an integer n in polynomial time, assuming you have enough information about the bits of one of the prime factors. And so you have to have either one of these two scenarios. Either the lowest 50% of the bits of P are known, or the highest 50% of the bits of P are known. Right? So if you leak the information in that specific way, Coppersmith has developed an algorithm which will provably factor n in polynomial time. Okay, I'll go over the algorithm at a very intuitive level, just not into the details, just a summary of how it works. It uses two techniques. It relies on integer root extraction. So given a polynomial, find the integer roots, and lattice basis reduction. Who's seen lattice basis reduction? Anyone? Okay, so a couple people. All right, so a lattice here, it's really simple. It's basically a discrete subgroup of the Euclidean space. So in 2 dimensions, it looks like this. And you have this periodic subset of the Euclidean plane. Basically, let's say you take 2 independent vectors here, 3, 5, and 6, 0. You can take all integer linear combinations of them, and you get the nice point set, right? So these are all, the dots are all the lattice points. Okay, so this is known as a lattice. And lattices are very useful in mathematics and cryptography in particular. They're used all the time. And one of the primary reasons why they're so useful is because of this concept of lattice basis reduction, which I kind of demonstrate on this slide here. So basis reduction is essentially there's many bases of any lattice. Some bases are better than others. So some bases are actually relatively poor to work with. So an example would be the 2 blue vectors on the slide here. This is a bad basis. They actually generate the same lattice, right? Those 2 blue vectors will generate all the points in the lattice. They're not going to do it in a great way though, right? Because first of all, the lattice vectors are long. They're also like almost orthogonal to each other, right? There's very little angle between them. You'd much rather work with the red basis than the blue basis, right? Red basis kind of gives you roughly orthogonal vectors and the short vectors. Okay, so the reason why the lattice basis reduction is so effective is because we have algorithms which can provably find very good bases. They're not going to be the optimal basis, but they're going to be good enough for many applications. In particular, LLL, this was an algorithm from the 1980s. It will run in polynomial time in the dimension of the lattice, right? So as large as you can take n, the dimension is as large as you want, it's still going to run polynomial time in n. And it's going to give you a vector which is an approximation of the shortest vector in the lattice, the shortest non-zero vector. Okay, in this case, you would find one of the red vectors. Okay, so this is one of the lattice basis reduction is going to be used in Coppersmith method. Here's the intuition, the one slide summary of Coppersmith. Coppersmith finds a way of given a polynomial f, it finds all small modular roots of f, modulo of prime p, where p is actually unknown. This is what makes the problem difficult. P is unknown. You know a multiple of p. We know n, which is a multiple of p. But it actually finds roots mod p, right? Which is actually surprising, right? P is unknown. If you knew p, this would be easy, right? You can do, given a polynomial, you can actually factor it modulo p. You can definitely find the roots mod p. But if you don't know p, we just know a multiple of p. This is a very difficult problem. But Coppersmith comes up with this very clever way of finding not all the roots, but at least the small roots, right? So in absolute value, you can find all small roots of f mod p.
So it returns the roots, but not p.
Yeah, it's going to find the roots, but not p. But we're going to use it to actually find p. Yeah, so we don't know p here. That's the whole point. Okay, so how does it work? The way it works is you set up this clever lattice for which a very short vector in the lattice will correspond to a polynomial g.
So when it returns the roots, they are all for the same P.
Well, yeah, for any divisor of n. So in this case,
Okay, so it can be F mod P or F mod Q.
yeah, I believe
So it's a root of one of those.
Yeah,
two.
there's a bound, I believe, on, like in this case, P and Q are the same size, so it should work for both. But I think there's a bound in the prime as well. So, okay, so the way it works is from a short vector of the lattice, we're going to find a polynomial g, where g of x0 is actually a root over the integers. So this is not a root mod p, this is the difference, right? From a short lattice vector, you're going to find a polynomial g, which has an integer root x0. And then the problem is easy, right? We can actually, this is a known, there's efficient algorithms to find integer roots, right? So we can do integer root extraction on g. So we do a lattice basis reduction to find g, we do integer root extraction on g to therefore find x0, which is going to be a root. Okay, so does this allow us to find p? Here's how it works. So let's say we're gonna know the high bits of p. So I represented p by p hat plus p check. P hat is the high bits, p check are the low bits. Okay? Basically what Coppersmith says, if we know enough of p hat, if p hat is large enough, that means p check is relatively small, we can find p check from p hat. So let's say p is equal to, p will be 7583, where we split it into two parts. The high bits will be 7580, the low bits will be 3. Okay, so we're going to try to, this is just a toy example again, but the whole process generalizes. So from knowing p check, p hat, we're going to find p check. All right, so what is the polynomial we're going to set up? You set up this polynomial here. F will be p hat plus x. And this has a root, a small mod p root, right? Because f at p check is equal to p, so it's 0 mod p. Okay, so here is the lattice that we set up. Let's say n is the number to factor. It's a 58 million sum. P hat are the high bits of p. And then we set up our polynomial f, which is going to have the small modular root that we want to find. Now you associate a degree 3 polynomial with a vector of dimension 4 here. Okay, so this is an easy one-to-one correspondence, right? You just take the coefficient vectors and you basically you stick them into the lattice vector. And you look at some certain polynomials of shifts of f and the constant polynomial n. So they generate this lattice basis. So it's just like kind of linear algebra. You have vectors, which then you can stick together into a matrix. And what's going to happen? I just did this in Sage. You have the input basis on the left. Right, this is the basis that was generated by Coppersmith. You use LLL on it, which gives you the basis on the right, and you can see roughly the coefficients in the basis on the right are smaller, right? They're going to be smaller vectors, and you take the shortest vector that LLL produces, like the first one, it gives you a polynomial, which you can then find the integer roots. In this case, it's a quadratic, so it's very easy to find the integer roots. It actually has 2, 3, and 143. 143 is spurious here, but 3 is indeed the low bits, right? So you find the integer root, and then that gives you the low bits of p, therefore the factor of n. Now you factored n, you can read Dr. Evil's messages to destroy the world. Okay. All right, so why can't we just use Coppersmith in the scenario that we were actually in? Actually, so this was the scenario where all the leak bits were the high bits. In that case, we can factor in with Coppersmith. But actually the scenario I talked about, right, it was the bits were randomly distributed in the prime. So actually Coppersmith does not apply in this case. There are generalizations of Coppersmith, which will work when you have multiple chunks of these bits. The method doesn't apply in our scenario, right? Because it's actually going to be exponential in the number of chunks, right? So it only works if you have a really small number of chunks. So Coppersmith is not going to work in the scenario I described, but this is where the SAT solver comes in. We're going to use a SAT-based approach with Coppersmith as a subroutine. Okay, so this is how the high-level summary of how the algorithm works. We're going to have, well, how do SAT solvers work? The way they work is they are assigning some of the variables to be true, some of the variables to false. Other variables will be left undefined, right? And it keeps us taking a variable which is undefined and either assigning it true or false And then it keeps going, deriving consequences of that. And eventually it's going to reach a stage where it's either to find every single variable to be true or false, in which case you find a solution, or what tends to happen is eventually you kind of back yourself into a corner, right? It's a bit like playing Sudoku, right? You make a guess for one of the numbers because you can't make any more progress. But once you make a guess, you can make progress, and eventually you might realize, oh, the guess was incorrect, right? What do you have to do? You have to backtrack. You have to undo all the consequences of the guess, try another guess. So this is what the solver is constantly doing, right? It's constantly making guesses, deriving consequences of those guesses, and if it has to backtrack, it goes back and undoes it, and it keeps doing that until it finds a solution or is able to prove it's exhaustively searched the entire space. Okay, so in this case, there will be a solution, right? We know there is a prime factorization, and at some point in that whole process, we can be in a scenario like this, where let's say we know, or we've made guesses for at least for the low bits of P. So the low bits of P are 1, 1, 0, 0, 0, 1, 0, 1. The high bits of P are unknown, right? They're question marks. So what the solver would do by itself, the SAT solver on its own, would then try to assign 0 or 1 to the question marks, and eventually it's going to keep doing that until it has a full, if it's found all of the bits of P. But we can use Coppersmith in this case, because remember, Coppersmith will apply when you have all the low bits of P. You need at least 50% of the low bits of P, and you can apply Coppersmith in a polynomial time to derive the high bits. Okay, so in fact, this is going to work. There's two cases to consider here, because the first case is the easy one where the low bits of P were assigned correctly. Well, in that case, Coppersmith will just give you the high bits of P, and you're done, right? High bits of P gives you the full prime P, and then that's a factor, and you factor it in. Now that's when you got lucky, right? The solver made correct selections for the low bits. The typical case is at least one of these bits here, and the low bits were assigned incorrectly. In that case, well, Coppersmith won't find the high bits, of course, but it will tell you information. It will tell you, because Coppersmith you can prove always works, right? If you give it the correct low bits, you can prove Coppersmith will derive the high bits from those. So that means if you gave it bits which it wasn't able to extend, that's a proof that those were incorrect bits, right? If you didn't find a factor, you have to try a different selection of the low bits. So this is actually information the solver can use to speed up the search, because on its own, the solver would start trying to assign zeros and ones to the question marks. But let's say Coppersmith failed. That's a proof that there are no ways to make the question marks. Don't even bother trying any possibilities for the question marks, because it ain't going to work, right? So it tells the solver to backtrack early. This is the idea behind this kind of, you can think of Coppersmith as an oracle, which kind of tells it, try another path. So we can backtrack early. Okay, so our intuition was that this is going to speed up the solver, because even with the overhead of Coppersmith, it's a polynomial time oracle. So, it should allow the solver to backtrack early and speed it up. Well, we didn't know for certain, but this was what Yamin's thesis project was. So what he did was he implemented Coppersmith inside of the solver MapleSat, and then we just tested it, right? It's easy to generate a bunch of random instances. You can vary the bit length of n. You can vary the percentage of leaked bits that you're providing as hints to the solver. And we did this for varying parameters. We took 15 random instances in each case and then took an average, right? I'll show you the data on the next slide. And it was implemented using this library called FPLLL. It's kind of the state-of-the-art lattice reduction library. And you have to make a judgment call of how often you want to call Coppersmith. In our case, it turned out to be prudent to call it when you have 60% of the low bits of P. Essentially, this just allows you to keep the lattice dimension size low. You can prove it with 60% of the bits. You can actually work with a fixed lattice dimension of just size 5. So lattice is very small. Lattice reduction is very fast. And this is regardless of the size of n. So the problems we consider, this was a good trade-off. Okay, so here are the results in summarized plot. You have the blue dots are SAT plus Coppersmith. The orange dots are pure SAT solver alone. And the solid line there is the median of the 15, right? So you can kind of see the kind of typical case. And this is on a log scale, right? So this is, as the bit length of n increases, you move to the right, the running time is exponentially increasing. This is with leaking 50% of the bits, okay? However, this also means that the gap between the orange and the red is, it's an exponential speed up, right? Yeah, they're both of them are running in exponential time, but the blue is a slower growing exponential. Okay, so it just means you can go that much farther, right? We're able to get up to even 1600 bits, where the pure sat solver kind of tops out around 700 bits or so. Now, if you wanted to compare this with the number field sieve, just for sake of comparison, right? Again, this is not totally fair, right? The number field sieve is kind of at a disadvantage here. It doesn't use the leaked bits at all, so it just reduces to a pure integer factorization problem. But just to give you a sense of how much faster this is with the leaked bits, for 512 bits, the number field sieve would run around 3,000 hours, and we're able to do it in with Coppersmith about 100 seconds, and with the pure set approach is around 1,000 seconds, right? So with Coppersmith, it's like a 10 times speed up and much faster than the number field sieve. In this particular case, when we have leaked bits, this is a similar plot, except we kind of flipped the independent variable here. This is when you fix the size of n to be 256 bits. Okay, and then we change the percentage of bits which are being leaked. And you can see here, you can essentially, with sat solving alone, pure sat solver can solve problems where you leak 45% of the bits, whereas with Coppersmith, you can get solve problems with 35% of the leaked bits, right? So, but again, the running time just kind of really takes off. The less bits you have, the running time just kind of explodes. So there is definitely a gap here. And we compare it against the one approach that we could find code for in the literature, which was a branch and prune approach. And there was an interesting paper, right? They are actually able to prove, subject to some conjectures, which are plausible, that with this branch and prune approach, if you know 57% of the variables or more, right? So 57% or more, the approach actually runs in polynomial time, right? And you can see actually this 57% seems to be an inflection point where even our approach seems that's where it kind of starts becoming an exponential time search. But with 57% or more, they're able to prove this branch and prune approach runs in poly time. Of course, you can run their code for less than 57%. It's not going to run in poly time, but you can try it. So we did, with 40% leaked bits, it took around 2,000 seconds, where we were able to do it in about 100 seconds. So again, the SAT plus Coppersmith was faster. This could have been partly due to the fact that the branching, in their code, they just stored all the branches in memory, which turns out to really blow up the memory usage. Sat solving, one of the tricks of sat solving is the solvers are very well tuned to use a little, they're very cognitive of their memory footprint, right? So the solver here uses at most half a gigabyte of RAM, right? They're constantly kind of keeping the memory usage down because that speeds up the overhead of the solver. Okay, so I just want to summarize with pointing out this is not an isolated incident. I've been working on SAT plus computer algebra for about a decade now, and I see the same sort of behavior quite frequently in the problems I encounter, right? You might have an exponential time algorithm for computer algebra and SAT, but when you kind of can combine, they're kind of orthogonal techniques, right? The SAT solver is very good at search, right? Search problems, whereas the computer algebra system is very good at mathematical algorithms, right? They have really clever algebraic techniques that can really be helpful. SAT solver has no knowledge of them. On the other hand, the computer algebra system hasn't really been tuned to use kind of the engineering on making search really fast, right? So we're actually able to solve lots of different types of problems faster than you would otherwise, right? It still might be an exponential problem, but you can go, if you decrease the base of your exponent, you're going to make the problem, you can push the wall that much farther, right? So if you are interested in this sort of paradigm, I did write a survey article for Communications of the ACM, published 2 years ago. So you can, I linked it here on my slides. They'll be on my website, and I'll be happy to take any questions now. So thank you so much.
All right. Thank you. So we usually give the Zoom audience the first crack at questions. Is there anybody out there that wants to jump in?
Yeah, thanks for the talk. It was a really cool talk. Thanks for making it so interactive too. Do you think that RSA cryptography is actually gonna be Trump soon? Because crypto is really coming about, right? Do you think we're gonna need like new banking information, or like are we gonna get hacked soon, or?
Well, that's always the kind of faith that you have, right? Because RSA, we know it will be broken by quantum computers, but there's no proof that integer factorization is difficult, even for classical computers. So maybe tomorrow someone comes up with a fast classical factoring algorithm, which totally breaks RSA. Hopefully that's not going to be the end of the world, right? Because there are these post-quantum cryptographic schemes, which are thought to be provably secure. But even that, you're placing your faith in something, right? So yeah, I think there will be a push to move away from RSA. It's held up remarkably well. A lot of crypto systems that are proposed get broken pretty fast. RSA has been around since when was it? 77, yeah, so 50 years almost, right? So, and it's still, if you do it right, it seems to be secure, but it won't be for once quantum computers are around. So it probably will get depreciated.
More Zoom questions?
So when you're running sorry, Zoom questions.
Yeah.
No, I think there's not.
So in the process of running like the SAT plus the Coppersmith,
Coppersmith is
Coppersmith, you can find out a way that you can essentially check if your lower bits are correct or not, right?
Yeah.
How does it then iterate into the next cycle? Does it just randomly choose another assignment, or is there a smarter way to make that choice?
Yeah, so another one of the tricks of the SAT solving, why they're so good in practice, is they have heuristics for what variable to choose. This is extremely important.
Yeah.
Right? What variable do you want to choose? And sometimes it's a bit mystifying, like what variable they choose. In this case, it seemed to be, they're choosing at the low bits. We just kind of observed the solver was deriving mostly from the low bits.
Okay.
So, but yeah, it's just going to learn it's like backtrack early. It's going to make another assignment. It tended to be on the low bits, but it was jumping around.
Oh, based on like the most previous backtrack, or?
Yeah, well, it backtracks it has a heuristic on how far to backtrack.
Okay, gotcha.
Because yeah, it doesn't just go, the last.
Yeah.
It'll backtrack sometimes, just a couple steps. Sometimes it'll just restart the search from basically scratch, keeping the knowledge that I already learned. But yeah, so it's a lot of engineering effort and heuristics of how far to backtrack and so on. But that's one of the advantages of using a SAT solver, because all this has already been worked out. You're probably not going to beat. You're probably not going to write a general purpose search faster than a SAT solver. Like maybe for your specific problem, something that you can outperform the SAT solver with, right? If you put enough time into it. But are you going to put enough time when compared to the decades of work that was gone into finding these good heuristics? It's not pragmatic, right? That you can use all these heuristics which are already there, which tend to perform well. So.
Awesome.
That's a good point. Yeah, I think, this is also why we advocate for integer programming a lot, right? I mean, there's just a huge investment there. So if you can formulate an integer program, even in a clumsy way, often you can solve it, even though it's NP complete.
Sorry.
Honestly, even continuous solvers, they are very good also. Like the continuous optimization.
Yeah, well, right. Yeah, you mean like the sort of
Because, I personally find it surprising because you can write lots of discrete math problems as continuous optimization problems, which is something that you would not immediately think about, right? Because it's discrete and continuous, right?
Mhm.
But I've done this like searching for other Mart matrices, which also Curtis has a good background on that, and it's actually works very well,
You
surprising.
can also do like vertex covers and independent sets as continuous problems.
Yeah.
Mm.
Sorry, excuse my ignorance on this. You said the Goldsmith always guarantees that you can find this.
Go down with your metals. It's only copper.
Copper. That it's to find these roots, modulo P or some integer multiple of modulo P, right? That are smallest in absolute value. Is there ever a chance where that doesn't work, or does it always find the smallest ones?
No, like it'll find small ones to some bound, right?
To a bound. Okay, so there are instances where it could just not.
Yeah. If your root
Yes.
is too large, it's not going to find it.
Gotcha, but that still inherently also gives you information about the problem, about these roots, or no?
I mean, you can reduce integer factorization to just finding roots modulo n, right? In fact, that's how the number field sieve works at its core. You're actually you're trying to find roots of x squared minus 1.
Oh,
It's a
okay,
simple
okay.
polynomial like that.
Yeah.
It's hard to find unless you know the factors of n.
Mhm.
It's hard to find modular roots. of polynomials in general.
Yeah.
But Coppersmith allows you to find very small modules.
Small ones up to a tolerance. Okay, thank you.
Have you thought of the discrete log? Which,
Yeah.
there are lots of analogies, right? Or not analogies, but they're kind of same level of crypto.
Yeah, as far as we had a question about this, and I think Coppersmith applies to factoring specifically, which is kind of interesting because there are a lot of, like number field sieve can be applied to discrete log as well. There's a reduction, right, where you can actually reduce factoring to discrete log. But I think this is a factoring only type of method. So, but it would be interesting to try to apply to discrete log problems too.